Okay. All right.
And then we still have epoxidation and ozone analysis for alkenes.
Okay. For epoxidation, what are your reagents?
Peroxy acid.
Okay. So which one do you guys like? Which one did you put on your note cards, or did she just, how did she have you draw?
She had us go R to a carbon, which is double bonded to an oxygen, and then single bonded to an oxygen, which is single bonded to another oxygen, which is bonded to a hydrogen.
Okay. And what else?
That's it.
The peroxide? No.
Does it have heat or anything with it?
That's a good question. I actually don't remember.
It's page 259.
I think it is.
I think it is just. I think it is just peroxy acid. Okay. So,
That sounds crazy.
yeah, this one has an intense looking transition state in the mechanism, but what do you know? What does it produce? What are its characteristics?
Produces an epoxide and acetic acid.
Okay. So, and I mean, we're reacting with this alkene, so you know it's going to make an epoxide. There's only one place to make the epoxide, but what's it going to look like?
Triangle.
With, yeah, right?
Mm-hmm.
Okay. Is there anything else you want to go over with that one, or is it just one of those you probably should draw a few times to get the transition state down? Okay. All right, and then you said hydrogenation oxidation?
Ozone analysis.
Right. Did we skip? Oh no, we did hydrogenation oxidation. Sorry.
That's the BH3, right?
Uh-huh.
The two-step.
Yep. Okay, so what do you need for ozonolysis? This one's nice because the name kind of tells you something.
You need ozone.
Okay, good.
Zinc and water.
You need what, sorry?
Do you need zinc and water?
And,
So we have to label this as a two-step?
yes.
Okay.
Yeah, so which is, you know ozone is involved in the first step. Is there anything else in the first step?
No.
Okay. So then you react it with ozone, then you react it with
Water and zinc.
water and zinc.
So she told us we didn't have to know any of the mechanism for this, but why is the zinc even there? Like, I don't.
That's a good question. Because it seems like in 351 you don't deal a whole lot with metals in your reactions, like you did with hydrogenation. You had a metal catalyst, right? And there's metal. I'm assuming it's a catalyst because it's not involved in the product. But in 352 it seems like we use quite a few metal catalysts.
Okay.
So I remember learning when we learned this mechanism that they don't really understand the mechanism perfectly, which is why I think our teachers aren't making us memorize it. But I assume it's just a metal catalyst. It just somehow is helping the reaction along.
Okay.
So I don't know. That's a good question. So what's it going to look like? What's the characteristic of ozonolysis to an alkene?
Our carbons are gonna. That double bond's gonna split in the middle, and then there's gonna be oxygen bonded to those carbons.
Okay. So tell me if I'm drawing what you're saying. Is that what you're thinking?
Yeah.
Does that look right? Bart, you said something it's kind of how I remember it, but do you want to explain what you're saying? I'll draw it while you're talking.
So you just cut the double bonds in half, and then put oxygens there where that squiggly line is on both sides.
Good. Brother Sargent, when he taught us this, like kind of explained it like this. Yeah, it's like you're breaking that double bond in half and just like stabbing each end into an oxygen.
Okay.
So I don't know, it helped me remember it, but makes sense. Okay.
Sorry, could you draw that result one more time? So just the double bond, and then was there a branch coming off the back of those?
No.
Just 2 double bonds with oxygen on the end of them.
The example she used.
Sorry, I can just space them out a little.
No, I'm just wondering why does this one keep a tail and that one doesn't?
Because that's what's still on the left side. So you're
You
just
have to have
splitting
3 carbons still.
Mm.
So you just split the double bond in the middle, and whatever's on the left side to begin with still is on one of them, and whatever's on the right side still on one of them.
Okay.
So is it, so like in the example she used, it was 1 carbon structure. Whenever like this happens and there's both oxygens are on the same carbon structure, we can assume that came from a cyclic.
Yep.
Oh, yeah, because if it was linear, like
It
this
would,
was,
it would form 2.
2 molecules.
Okay.
If it ends up, you run it through ozonolysis and it ends up being a chain with 2 of these carbonyl groups, then it was cyclic.
Okay.
Yeah.